Finally, let's talk about one specific class of matrix functions called quadratic forms and how this relates to matrix properties like the definiteness of a matrix. A quadratic form is a function which takes as inputs vectors in Rn and outputs a scalar value. And it's defined as f of x equals x transpose times A times x for some matrix A which is n by n. So hopefully it's obvious that this does produce a scalar value because x transpose is 1 by n, A is n by n, and x is n by 1. So this is a valid matrix product, and the resulting size is going to be the outer dimensions, which are 1 by 1 here. Now if we use the definitions of matrix multiplication, what we'll see is that this expression here is actually equal to the sum from I equals 1 to n and the sum from j equals 1 to n of aij times xi times xj. That's just plugging in definitions for matrix multiplication. What you'll get is this form here. So you should think of this as somewhat of a generalization of quadratic functions for scalar values. So if x is scalar valued, then a times x squared for some coefficient a would be a quadratic function of x. And more generally, when x is a vector, this quadratic form here has aij being the coefficient of the product between xi and xj. So we're multiplying all possible combinations of xi and xj and multiplying them by the coefficient aij, then summing these all up. Now interestingly, we can take A to be symmetric since this form we can write x transpose A times x. Well, this is just a scalar value, so it's equal to its transpose. And for a transpose, remember to multiply, take the transpose of a matrix product, we transpose each term individually and take their product. So this transpose here would be this thing in flipped order with every element transposed, which would be x transpose times A transpose times x. And of course, this is the same thing here, just with A transpose instead of A in the middle. So this is also equal to 1/2, x transpose times 1/2 of A plus A transpose times x. But importantly, this matrix here, A plus A transpose, will always be symmetric. And so we can always think of these quadratic forms as having a symmetric matrix A. Now let's give a few definitions. We say that a square matrix, n by n, is positive definite if and only if its quadratic form is always greater than 0 for all x not being equal to 0. Similarly, we say it's positive semi-definite if it's always greater than or equal to 0. And here we can actually let x equal 0 because it's just greater than or equal to 0 for all x. Similarly, it's negative definite or negative semi-definite if this is less than 0 or less than or equal to 0 for all x. And we call it indefinite if it's neither positive definite nor negative definite. Neither positive nor negative semi-definite, rather. Now, as a simple example, let's take some of a positive definite matrix here. Let's take a matrix B. Actually, we'll just define it so that it's positive semi-definite, though with a couple extra additions it could be positive definite. Let's take B to be just some matrix M in M by N. And let's look at the matrix B transpose times B. Well, if we take this quadratic form here, x transpose B x, this whole thing here is also equal to the L2 norm of B times x squared. And we know from the L2 norms, it's just a sum of squared values. This is always positive, or at least always non-negative. So this term is greater than or equal to 0. And what that means is that B transpose times B is positive semi-definite. Now it turns out we can characterize definiteness of a matrix by its eigenvalues. This is another very useful property of eigenvalues. In particular, A being positive definite is equivalent to all the eigenvalues of A being strictly greater than 0. Similarly, positive semi-definite says they're all greater than or equal to 0. Negative definite says they're all strictly less than 0. And negative semi-definite says they're all less than or equal to 0. This is a very easy property to show. Let's take the matrix A and form its eigenvalue, eigenvector expansion, decomposition. Remember, A here, for a quadratic form, we're actually going to assume that A is an n by n matrix here that is actually symmetric. Remember, because for quadratic forms, for the notion of A transpose, rather X transpose AX, we could always just take A to be symmetric, so let's just assume A is symmetric here. That's what matters in a quadratic form. That means we can write A as U lambda U transpose for an orthogonal matrix U. Now let's look at the product X transpose U lambda U transpose X. For any X, let's just call this product here, X, remember, is X transpose will be, in this case, 1 by n. U will be n by n. So let's just call this product here Y transpose. Rather, this thing here is just Y. So this expression here, the quadratic form of A, equals Y transpose lambda Y for some vector Y, where Y equals U transpose times X. Now, interestingly, for any X, we can come up with a corresponding Y, and for any Y, we can come up with a corresponding X. And this holds because U here is an orthogonal and therefore invertible matrix. So this thing, being positive for any Y, is equivalent to this term here being positive for any X. But this term here is just equal, because this is a diagonal matrix, this is equal to just the sum from I equals 1 to n of lambda I times yi squared. So this whole term here has to be positive if all the lambda I terms are also positive. And that shows that if these lambdas, the eigenvalues of A, are all greater than 0, this product here will always be greater than 0, and so A is positive definite.